of memory from the DRAM to the processing, right? So this is the so-called neuromorphic architecture the whole community is trying to go to, right? So in our traditional computing architecture, we call for Neumann. It's computational centric. In the past, we feel think computation is slow, right? So we have a CPU. We keep improving it. We make it very fast, from 1 micron to 1.13 micron to 90 nanometer, now 40 nanometer. A lot of function, right? From thousands of transistors, and now we're talking about tens of billions of transistors. It can do a lot of stuff. And since then, we have been using this architecture. We have a memory next to us. It can be SRAM. It's pretty close, pretty fast, but still not good enough because SRAM has very low density. And then we also have DRAM. Remember the hierarchy I showed you last time? Every time I need to take a lot of memory. And now we are at the point we have the memory war, right? Well, I want to do computation. I'm so smart. I can do the addition, multiplication so fast. But you just cannot supply me enough data for me to do the computation. Then what's the point? So because of this, people say, why don't we emulate our brain? Can we put the memory inside the computation? Just like this, neuron synapse, right? Not exactly like this, but this is a regular one. The point is that we have the device to do the computation and the memory at the same time, like our brain, right? When we do computation, although sometimes say, oh, let me think what I learned last time. But this is not really you try to fetch something from a memory. Actually, I don't know, maybe it is. But it is not this one, right? So the point is that this is data-centric, no longer computational-centric. And we call it neuro-inspired, right? So this is the first point about neuromorphic architecture. You put the data, you put the memory and the computation together, right? So this is memory plus computation. Any questions? Now, so if you want to build this, yourself, I can hear you.
Very good, specifically.
Okay, I muted you. Please unmute yourself if you have questions. Now, so how do we do that, right? We actually difficult to do that. Actually, what can we do? We use the emergent memory. Look at this one. It kind of reminds you of something. This looks like a crossbar. And we talked about crossbar before. So maybe we can do something like this. We talk about STT-RAM, spin-tau transfer. We talk about resistive memory. We talk about PCM. Ferroelectric memory, we did not really discuss much, but it's just the same. But we mostly emphasize on the negative capacitance as a transistor, right? So why they are good? The first thing is you want to make it small. They are tens of times smaller than SRAM because they are crossbar. Remember, they're so neat. Only two metal lines running vertical, perpendicularly, and then you have a right. You have two lines running here. My drawing is not good. And then you have this structure here. Right. This is the structure of the memory. And you do it in a crossbar fashion. So every point is a memory and maybe is a computing unit. So this one can make it very dense. And besides this, for each point, before we only talk about on-off, we actually can program them with multiple bits. So instead of high, resistive state and low resistive state, right? Which give you 0 and 1. I can have different value. For example, let's say 1 ohm, 10 ohm, 20 ohm, to 100 ohm. Let me only use 80 ohm. Then I have how many level? Actually, I should not start with 1, just 10 to 80, right? Then I have 8 level. 8 level give me 3 bits. So with 1 memory there, I can store 3 bits. Okay, and we can do parallel update. When I remember last time I showed you how to parallel update the resistive memory, right? You just apply V on one side and then 0 on another side. All those bits that you want to apply V. All those you don't want to update, apply V divided by 2 on both terminals. And most important, they're non-volatile, right? We never power us off, but at least we know that when we sleep, the next day we won't lose our memory. Maybe they still have some minimal power, right? But based on our understanding of the neuron, I believe that if we put the brain in 0 Kelvin and then heat it up again, the connection is still there. Everything is still there, right? So it's non-volatile. So these are all the good things for neuromorphic computing, right? So you see that in order to do this, we want to have a small dimension. We want the dimension to be small. We need multi-level. We want to have a large dynamic range, right? For example, you can go from a very low resistance, right? Let's say from 10 ohm all the way to 80 ohm, right? It also needs to be symmetric and linear when we're doing the update, because we're going to change the resistance of this component. But most importantly is that I want to update them with very low energy. We want them to be low, right? Think about if I need to update with high energy, then it's useless. I not just want to have a high density, I also want to have a low power consumption, right? And you need to be able to update many times. Right? And also store for a long time. Indeed, for our brain, this is not the case, right? We can forget things very quickly for short-term memory, right? But for this, we are okay. We can do it for a long time. And even for human being, I also don't think that we can update too much, right? Yeah, I don't know, right? If you keep seeing something yes and no and yes and no, right, that you will get crazy if you try to update many times. But for the real neuron, for the neuromorphic computing memory, we need this. Okay, this is just a list of the requirement. Any questions? Now, then let's start. I only want to give you 2 critical concepts in the neuromorphic computing that many people mess up, okay? The first one is so-called machine learning and deep learning. This is the first type of so-called neuromorphic computing. This is first type. This is not imitating, not exactly how the brain works. Okay? It's not exactly how the brain works. It is to but make deep learning faster. Now, I cannot say that this is not imitating our brain, because in machine learning, I don't know if all of you have learned some sorts of neural network before. The machine learning, you see this weight, right? Let me give a brief introduction on machine learning on neural network. Basically, you have this input, and it has a lot of vector. It has x1 to, it has a vector with many value. It's a vector, right? X equals to x1 all the way to xm. In machine learning, we also have a post-neuron layer. And how do they calculate? For each connection, we actually have a weight. For example, this is W11. This is W12. And this A1 is what? AI is equal to something, we call this an activation function, right? And we don't care at this moment. This is activation function of summation of this xj. You have this, all this input, right? Each xj times ji for j equal to 1 to m plus something called bias. Now, maybe this is a little bit, if you learn machine learning already, you know what I'm talking about, right? If not, let's look at an example. For example, what is A1? A1 equal to an activation function taking what? X1 times W11 plus, what is this 9? This is W21, right? X2 times W21. And how about this 9? This is W31, right? Plus X3 times W31 plus all the way to XM times WM1. And then we plus something called bias term, right? This is the bias term. Ignore it. I did not put here. There is something called bias. Let's say this is BI. We did not put here, but this is not too important to illustrate the concept. So do you see that? What is a neuromorphic computing? Now, first of all, this type, why did people come up with this thought? This is related to our brain. Think about this is the 7,000 pre-synapse neuron, right? They all fit to this neuron, A1. I have 7,000 connections. They all fit to here. And each of them has a special weight. Some are very heavy. For example, W11 may be very large. So X1 times W11 will be really big. Then it's affecting me. If W21 is 0, then whatever in X2 is not affecting me. This is just like our brain. We're connected to 7,000 neurons, presynaptic neuron. Okay, a few of them is very strong. So whatever signal comes in is going to make this value very large. But some of them are very weak, has very weak connection. So that's why whatever comes in, because the W, the weight is small, then it's not affecting me. Right? So that's why this is like how our brain is working. But this one can be implemented in the machine already, in CPU, right? But now you see that what is this? What is this type of operation, right? I skip this sigma, activation. Activation is a function saying that, okay, if this one, for example, I use a simple one. If this one is positive, then I just keep it. If this is negative, I just give 0. So you see that it is like, I learned something. It all depends on the total sum and their strength of connection. It's just like my father say something, wash the dishes. My mother say, don't wash the dishes. My wife say, wash the dishes, right? maybe my wife's connection is much stronger now, right? So it has very large W. So even my father or my mother, let's say they both say, don't wash the dishes, they have very small weight. And then I will only put my wife's one is 1. Then it's going to activate me, right? Then I'm going to wash the dishes. It's just like this, exactly like this. But what is this one? This is nothing but just a matrix multiplication. Do you see that? This is an activation function, but then you're just doing this a matrix multiplication, Wji times a matrix, that's Xj. Yeah. If go back to try it, this is a matrix multiplication. So what is the problem? It means how many multiplication I need? Just for this activation function, I need to do m multiplication. And then I need to do m addition. That's a lot of computation, right? Oh, so that's why it's so slow with CPU. Great, and that's why NVIDIA is so rich now, because they used to produce the GPU. GPU is for computer graphic. Computer graphic is nothing but matrix multiplication, or the transformation of the figure in your screen, whether looking at certain angle, rotating, the people running to you, you moving. These are all matrix multiplication because it's just a change of coordinate. So that's why NVIDIA is just is so successful, because their GPU is good for matrix multiplication when the machine learning comes. So when we have this AI big data, everyone want to buy GPU because we do a lot of this matrix multiplication. And when we do a lot of deep neural network, remember, this vector can be thousands image, different color, right? Thousands of image, thousands of pixels, each them is a pixel. And then you have many layers. So you are talking about gigabytes of data doing those type of multiplication, okay? But nowadays we say this is not enough. So what should we do? Neuromorphic computing. So this one, we are imitating the brain. But when we talk about neuromorphic computing, this is the first type. We actually try to do this matrix multiplication by using this array. Each of these can be, for example, a resistive memory, a PCM, whatever. We can change their weight. What do we mean by weight? Change their resistance. But here I don't say that is a resistance. I say it is a conductance. For example, this one, connect V1 to I1. What is this? This is W12. And it has a conductance of W12. Okay, so this one is W free because it is free here, and then it is going to be the current free. Then this is G free. So what I'm trying to do? Let's look at one of the branch. When here I say 1, they are granted. We are trying to see what is the current going into here. For example, what is I free? Well, if you look at the path, I free can be this. The current go from V1 and then go through this resistance and then go down. This is 1I. Current go through V2, go through this resistor and then go down. And all the way current go from Vm, go through this resistor and then go down. So I free is just the summation of all the resistance from J equal 1 to M of all the current. But what is the value of the current? Ohm's law. It is just Vj minus 0. Isn't that right? This is 0, right? So the whole line is 0, right? We assume this is ideal. So it is just a potential difference across the resistor divided by the resistance. But I don't want to do divided by resistance. I use conductance. Multiply by conductance. So this is equal to what? Summation J equal to M Vj times Gj3. Now, can you try to compare these two things? What is this? Right? Let's only look at this. Bias is just an extra. We can make it into weights. I don't want to go to details, right? Isn't this is just the same as the green box? Right? Where I equal to 3, right? I can make it more general. This one can become anything I, right? Now I'm talking about I3, now it can be I2. So this is I, right? This is I. You see that by doing this, if I encode the input voltage as the extract, for example, in your machine learning, this is the pixel strength. I make it into Vj, scale it accordingly. And then I encode the weight as G3. Right? Maybe I should swap this one. Right? So whatever weight you have, whatever weight you have, I just put it, I scale it as the conductance. How am I going to compute this? I only need this one, the whole thing, one computation. I should say one step computation. Right? Correct. I apply the voltage here. Then I get all the I and also parallel. Think about here. I want to get A1 to AN. I need to repeat this N multiplication by N times if I only have one CPU. First, H1 times W11, H2 times W21, all the way Xm times Wn1. Okay, I got N multiplication. Add them together. I got A1. Then let's go to A2. X1 times W21, X2 times W22, all together M times. So ideally, I need N by N multiplication, right? For all, I need N by N multiplication, right? We just ignore addition, which is very expensive. Think about if I have 1 million and 1 million, we won't be so much as that is two. Because we don't only work on one figure. We actually may take millions of pictures to do the training, for example, right? But here, let's say 1,000 pixels by 1,000. This is okay, 1 million multiplication. And then we need another 1 million of data to do the training. But here, you do 1 million multiplication, I only do one calculation. That's it. Only one. And also, what is this? This is an analog computing, right? We are not doing digital, just Ohm's law. So this is what we mean by deep learn, neuromorphic computing, right? It is not really thinking our brain. It's just to map the matrix multiplication unit in the machine learning. Of course, machine learning is based on the idea of our brain. So this is the first type. Any questions for this one? I hope that you understand what I'm talking about. So I hope that you let me know if you have questions.
So I have a question on the last lecture about STDP.
Oh, okay. That one I'm going to discuss one more time. How about for that one? Let's wait until later. How about for this slide? Any questions? Very clear to you? If I ask you to write down the equation in the exam, will you be able to do that? I probably won't, right? But okay, good. No questions? I assume that I did a good job. But anyway, so here is more just clearly to show you what if we have many layers, right? This is still the first type that I'm trying to do. When people talk about neuromorphic computing, this is the first type. And this is the research I'm doing also, right? I'm doing this type of first type. Only just use resistive memory to replace this MAC. We call multiplication accumulation unit. I forgot MA what, right? You have multiplication, addition is called accumulation. You multiply, accumulate it, eventually you get a number. Okay. So here we another activation for now. So now you have more layers, right? So if I give you a picture, if let's say I training, if you don't know, you have not learned machine learning, training of neural network means to find out the good weight that give you the right prediction. And basically training is there to find the correct conductance in the neuromorphic circuit. So once you're done, I give a new picture, then you do computation, a lot of multiplication, addition, multiplication, addition, and then eventually tell me, oh, this is a cat or a dog. We can do it pretty efficiently in this crossbar array, right? So here show you what I just mentioned. We put the voltage here, and then we have the conductance. So basically, this is the currents that you are getting is just the sum of this voltage times the conductance. Okay, so we start with the first layer, M1 to Mn, right? And then it is going to sum up to be the current. But then we need to convert the current to voltage. Here it did not show that, but we do need to do that. And once we reach here, then it becomes the input to the next layer, right? And then it again becomes the current. And then again, we convert the current to voltage. You come to here, then it becomes this P1 to PP, right? Here may be, let's say, handwritten digital digit recognition. It may be from 0 to 9. Then it will give some value. Maybe one of them will be the highest. Then you know that whether this image is 0 or 9 or whatever. Okay, if you are interested, take a look at this Nature paper. Right? They implemented it in hardware. Is this okay? Yeah, I think I'm quite detailed now, right? I hope that in the I wish someone told me like that, right? Before it took me a long time to figure out when I first studied this, because usually people just ignore all this detail in their paper. Now, so we are done with this one, right? But then another type, this is also the first type, but how do you, here basically you call potentiation change. Right? If I do neuromorphic computing, how do I change the weight? Right? This is the training part. Yeah. How do you do the training? If it is a CPU, right? You just put all this in the memory. I forgot to emphasize very important thing. Do you see that now? All these weights are at the same place as computation. Computation is what? V times conductance. And where is the conductance? The weight is stored as the conductance. So now, let me emphasize, not just one step, parallel, analog, and also the data is at the computation place, right? Right? We are not fetching any data from anywhere else. Very energy efficient. Think about this one if it's CPU. Where do I get this weight? It's all stored in the RAM and the DRAM. because we actually talking about gigabytes or hundreds of megabytes of weight data. Just look at people's AlexNet, whatever, right? Hundreds of megabytes of just the weight. We need to keep fetching. Here we don't have to. But how do we change it? We need to change the weight. This is the memory, right? How do we change the weight? If you remember what we discussed in the resistive memory, you apply a positive bias, then it becomes conductive. You apply negative bias, then it becomes less conductive, right? From high resistive state to low resistive state. But in machine learning, we cannot just have two levels, very conductive and not conductive. We want to bias it gradually. That is because we keep learning, right? The first time, let's say you forget to submit